Hello chemistry students, in this video I'm going to go over reaction type. Alright, so we'll probably come back to this slide and look at these reaction types again. Alright, so the first one we're going to talk about are synthesis or combination reactions, and that's where two or more substances combine to form a new compound. The easiest to identify is when you have two elements react with each other, because there's nothing else they can do other than combine with each other. So an example here is carbon and oxygen combine to make carbon dioxide. Remember, oxygen is diatomic while carbon is not, so that's why it looks like this. And here's the animation that shows sort of what's going on there. Alright, so the general form for that is you're going to have element A plus element B make something that's a combination of those two things, and you may have to draw Lewis structures or do charges in order to figure out what the formula for that compound will be. Alright, so in the synthesis reaction, two or more substances combine to form a new compound, and here's some examples of those. So like hydrogen and fluorine get together and form hydrofluoric acid, and sodium and chlorine get together to make sodium chloride. Okay, and then some of the more complicated ones like the metal oxide and water making a metal hydroxide, and the non-metal oxide and water making an acid. And we'll come back and look at those reaction types in the future when we're predicting reactions, but you can see all these involve two things combining to make a more complicated substance. Right, decomposition reactions are basically the opposite of synthesis reactions. So in a decomposition, a single compound breaks down or makes two or more simpler substances. So the general form here, AX equals A plus X. And here's some examples of that. So a binary compound, that's a compound with only two elements, breaks down and makes those two elements. All right, metal carbonates will break down to make calcium, or a metal oxide and carbon dioxide. Here's the reaction with metallic hydrogen carbonates breaking down. Now the thing that you should notice at this point is just simply that when these more complicated things break down, they don't always break down into elements. And here's one that you're probably fairly familiar with, which is the hydrated compound breaking, or the water separating from the anhydrous salt, and that would be as a result of heating. Alright, so we'll come back in a future video and learn how to use the reference tables to predict all of those things and do some practice. But for right now, we're just trying to get at the reaction types. Okay, here's a single replacement reaction. In single replacements, one element will replace another, or one ion will replace another. So for example, we got this element A by itself. It's going to come over here and replace element B in the compound. So an element in a compound gets replaced by an element that is not in the compound. Alright, watch what happens here. So more or less A switch places with B. So now A is in the compound with X and B is out by itself. Alright. Anions can also do this, so the negatively charged part, remember we always write positively charged things first. So like if you're trying to figure out, hey, what will this replace? Well, if this is a metal or something with a positive charge, it'll replace the first element in the compound. Or if it's negative or a non-metal, usually it'll replace the second element in the compound. Okay, so let's watch what happens with the anion, or the negative replacement. There you go. So Y switch places with X, and now Y is in the compound and X is out by itself. Alright, so general forms for those. In a single replacement reaction, one element replaces another. Alright, so metals can replace another metal, like magnesium replaces iron in iron chloride, and then afterwards magnesium is with the chloride and the iron is by itself. Notice that I did all this stuff balancing it and putting the formulas, writing those correctly. So you still have to do all that stuff, but just the general form here of what's happening is the magnesium replaces the iron. Okay, hydrogen can be replaced by a metal. So here's potassium, which is a metal, and it kicks kicks hydrogen out of the water, and so afterwards you get potassium hydroxide and hydrogen gas. Hydrogen can also, in an acid, can also be replaced by metal. A pretty common example of that is zinc metal can replace hydrogen in hydrochloric acid, and that makes zinc chloride and hydrogen. All right, and then halogens can be replaced by other halogens if the replacing halogen is more active, which we'll learn about in the next lesson. But here's an example of that. So fluorine is the most reactive halogen, and it will kick out the chloride. Remember, this is a nonmetal, so it'll replace a nonmetal or a negatively charged atom or element in the compound. So the fluorine kicks out that chlorine, and you end up with lithium fluoride and chlorine gas separate. Alright, double replacement reactions, instead of one thing switching, two things switch. So two ions will switch places with each other. So, and notice that, remember we always write the positive ion first and the negative ion second. So like the two positive ions will switch places with each other. Or you could think of it as the two negative ions switching places. So you'll end up, well, let's do that. So ion exchange. Alright. Now, let's talk about what cannot happen here in a double replacement. So, the negative ions are X and Y, and the positive ions are A and B. You would never end up with AB and XY, because positive ions are repelled from other positive ions, and negative ions are repelled from other negative ions. So, the only possible combination after a double replacement is that A ends up with Y, and B ends up with X. Okay. Alright, so the double replacements usually happen in an aqueous or water-based solution, and you form new compounds as a result. And one of those new compounds will usually be a precipitate, an insoluble gas that's going to bubble out of the solution, or a molecular compound such as water. The precipitate, remember, is a insoluble solid, so it'll form and settle to the bottom of the container that the reaction is taking place in. Alright, so double replacements where you form a solid are called precipitation reactions. Here's an example of that I would show you in class if we were in class. So lead nitrate and potassium iodide, both in solution, and they're both clear solutions. And afterwards they make this bright yellow lead iodide, which is a combination of Pb and I, and then potassium nitrate gets left in the solution. It's still aqueous. Okay, double replacements where an acid and a base react to form water and a solid are called neutralization reactions. And here's an example of that. So sodium hydroxide and hydrochloric acid. So the sodium and the hydrogen switch places. That makes HOH, which is water, H2O. And a salt, which is, this one in particular is NaCl, but you can make any, like there are other salts, ionic compounds that could form from an acid-base neutralization. Like say you had KOH, then you'd make KCl here. Alright, combustion reactions are probably the most mystifying to chemistry students. They're also probably the coolest to watch because that's burning and blowing stuff up. But they're pretty easy to recognize. So in a combustion reaction, something's going to burn. Usually these are identified as hydrocarbons combining with oxygen, releasing energy in the form of light and heat, and producing carbon dioxide and water. And this is important for you to realize that the products are always carbon dioxide and water. So here's our hydrocarbon. It contains carbon and hydrogen, And occasionally the hydrocarbons that we see will also contain oxygen. For example, sugar. One demonstration I love to do in class is burning a gummy bear, and the gummy bear contains sugar. The sugar contains carbon, hydrogen, and oxygen. Remember, sugars are carbohydrates, which shouldn't surprise you that they would contain a combination of basically carbon and water, so C, H, and O. But anyways, here's methane, which is a hydrocarbon reacting with oxygen. It makes carbon dioxide and water. Here's another hydrocarbon. This is propane, like the propane in a grill or a propane tank for heating somebody's house. That combines with oxygen and makes carbon dioxide and water. So the only thing that really changes amongst these reactions are the hydrocarbons involved, as well as the balancing of the reactions. So the general form here, hydrocarbon, oxygen, makes carbon dioxide and water. The products are always, 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 always carbon dioxide and water when you have a hydrocarbon combustion. Every now and then they'll sneak in a combustion to like a Mg plus O2 makes MgO, and that's not a hydrocarbon combustion, but it is a combustion because it's like a burning reaction. Okay, these can be hard for you to balance, but you practice that and just keep working at it. My suggestion when you're balancing these is to start with the hydrogen, and if you see as a result of doing the hydrogen that you have an odd number of oxygens, double the hydrocarbon and then go back and then balance again, starting with hydrogen. Usually doubling the hydrocarbon will make that odd number of oxygens go away if that's a problem, and then you'll be able to balance it. Also, when you get done with these, always check to make sure that you can't reduce the coefficients, because that's another common thing, is you might think you need to double it, but you really don't, and then when you get done you see you can reduce the coefficients to a lower whole number ratio, so go ahead and do that. Alright, and I think that brings us to the end of our slideshow. So thank you for watching, and hope you found this helpful.